In this screencast, we're going to use the Spock framework for creating and running unit tests. Let's start by creating a new project that's going to contain Java project code and use Spock to unit test that code. From the New Project window, we can choose any of these three options to create our JVM project. For this tutorial, we're going to use Gradle as our build tool. Spock is a Groovy testing framework, although we're going to use it to test Java code, so we could select Groovy here since we know we're going to need it. However, we can also add Groovy later on, which is what I want to show, so I'm not going to select it here. We need a JDK. I'm going to use JDK 11 for this project, but there's no functionality here that requires 11. You can use whichever version you're comfortable with here. Let's call the project Spock Tutorial. I'm going to save this to my default project directory. IntelliJ IDEA creates the files for the project and initializes the structure of the project. It's using Gradle to build this skeleton project to make sure all dependencies are downloaded and set up. Now the basics of the project have been created, let's take a closer look and set up the dependencies we need. IntelliJ IDEA added JUnit 5 as our default testing framework, which is a logical choice, but we want to use Spock instead of JUnit. Let's generate a new Maven artifact dependency for the libraries we want. I'm going to search for org.spockframework. We want to add the latest version of the Spock core library. This is the milestone 4 release of Spock 2.0 for Groovy 3. This is a test dependency, so let's change this declaration to test implementation. We don't need any of the other JUnit dependencies now, but we do need a dependency on Groovy, since Spock is a Groovy testing framework, so we need Groovy too. We're going to pick the latest version of Groovy 3 here. For now, we're only going to use Groovy for testing, so we'll also declare this as test implementation 2. Since we're using Groovy, we need to add the Groovy plugin to Gradle. Now we can load the Gradle changes with Shift, Command and I, or Control, Shift and O for Windows and Linux. And IntelliJ IDEA will download these new dependencies and correctly configure the project. With a mixed language project like this one way to organize the files is to keep Java code in the Java folder and to create a Groovy folder for Groovy code. IntelliJ IDEA knows about Groovy source sets because we're using the Groovy plugin in Gradle, so this directory name is suggested to us. When we're using the Groovy plugin, we don't need to specifically add the Java plugin as well, since all that functionality is included in the Groovy plugin. We might want to delete this line just to keep the noise down in our build file. We can keep the plugin to be explicit, or delete it to be more succinct. It's really down to our own preference. Let's start by writing a very simple test. From the project window, we can use the shortcut Command and N or Alt and Insert to create a new file. We want to create a Groovy class, since Spock tests are Groovy classes. We haven't created our package structure yet. We can do this when we create the file itself by typing the full package before the class name. Spock tests are often called specifications, so we'll call our test example specification. We want this to extend Spock's specification class. We can get IntelliJ IDEA to generate test methods for Spock specifications. This can be especially useful when we're not so familiar with writing Spock or Groovy code, as IntelliJ IDEA will generate the basic structure that we need. The method is defined with the def keyword, and Spock's method names can be strings. This is extremely useful when we're creating tests, as the text format gives us a lot of flexibility for describing exactly what we are specifying the behavior should be. Spock tests don't use an annotation or a specific test method name format to define which methods are tests. Instead, it uses labels. We'll see the different types of labels available to use throughout the video. For this simplest test, we're going to use expect. This can be used for defining the simplest behavior we expect to see. Spock also doesn't use assertions or an assert keyword, at least not normally. Instead, we can use simple checks, like the double equals. This method now specifies a simple expected behavior, that the number 1 should be equal to 1. It's not a realistic test case, but it shows the basic of a Spock test. We can run this test using the normal IntelliJ IDEA shortcuts, or the green arrow in the gutter near the line numbers. We can see that this test passes, which shouldn't be a surprise. Let's change it so that it fails. It's always helpful to see a test fail first to make sure it's actually working and testing the right things. When a test fails, Spock displays a helpful error message which shows exactly what failed and why. IntelliJ IDEA is using Gradle to run these tests, which is the default behaviour for a Gradle project. This is normally what we want, as it means our IDE is using the same process to run tests as the continuous integration or build environment is using. In a simple project like this one, where the Gradle build isn't doing anything extra like generating code or resources, it can be faster to use the IntelliJ IDEA test runner. We can find this in the preferences under Build, Execution, Deployment, Gradle, and we can select IntelliJ IDEA to run the tests. Let's fix this test and rerun it. Now it passes, and we can see it's not using Gradle to run it, as we don't have any of the Gradle output here. One of the most powerful features of Spock is how descriptive it is. It's not just for testing code, it's for describing and documenting expected behaviour. In our last test, we used the expect label to indicate a simple expectation. My personal favourite set of labels is given, when, then. Let's show this in a new test method. We use the given label to indicate that this part of the test method is setting up the conditions required for the test. For this test, I need a polygon with 4 sides. Polygon is actually a Java class. We can use Spock to test Java or Groovy code. Next, we want to say when. This is the thing we're actually testing, the behaviour we're trying to check. In this test, I want to make sure the number of sides has been correctly set. Finally, we say then. In this section, we're going to check all the conditions we expect have been met. In this test, I want to check that the number of sides is 4, the original number of sides I passed into the constructor. This test now reads like, given that I have a polygon with 4 sides, when we get the number of sides, then that number of sides should be equal to 4. Let's run it and see if it passes. It does, which probably means the polygon behaves the way we expect it to, assuming we wrote the test correctly. Using these labels might look like it's doubling the number of lines of code for a test method, but remember that tests often have many more lines of code in them, and grouping them in this way helps describe what's happening. While we're here, let's take a look at some things which might look odd if we're used to using Java to test Java code. Here, we're actually reaching right inside the Java class to inspect the value of a private field. We can do this from Groovy, which can be helpful for testing private fields or methods without compromising their visibility in production code. However, IntelliJ IDEA will give us a warning in case this is not something we want to do intentionally. Often, if we need something visible for testing, we probably will need it visible in production code too. Let's press Alt and Enter on the field and get IntelliJ IDEA to create a getter for the field. Let's go back to the test. Now there's something odd about our call to number of sides. The warning has gone and number of sides is no longer in bold. It no longer looks like it's referencing a field. In fact, it's not. If we hold down Command or Control and move our mouse over this, we can see it's actually referencing the method getNumberOfSides. If we're calling a Java getter from Groovy code, we can miss out the get at the start of the method name, and Groovy will still use the getter rather than the field. This can be useful to reduce noise, but you can still use the full method name with the get if you prefer. It depends upon what you think is most readable. Sometimes removing the get might be confusing. We've seen expect, and we've seen given, when, and then. But Spock provides a lot of flexibility around which labels to use and when. It's all about creating descriptive tests. In our last test, it did look like the labels might add a lot of noise for such a short test. The setup, for example, is very simple, and we could inline this into the actual test itself. Note that IntelliJ IDEA does support refactoring for Groovy code. Now we've moved the setup code into the test, we can remove the given label. When we rerun the test, it all still works as we expect. We have the flexibility we need to label blocks of code in whichever way we think is most readable, so the tests are documenting the expected behavior of the code. We've seen that we can write, run, and refactor Spock tests in IntelliJ IDEA. We can also install a plugin for extra support if we want. We need to go to Plugins, type Spock, and search the plugin marketplace for Spock plugins. Let's install this one. It's written and supported by a third party. It's not a JetBrains plugin. It adds some helpful behavior, like syntax highlighting for the labels, and inspections to help us see if we're using the labels correctly. Using this plugin is entirely optional. IntelliJ IDEA provides all the support you need to write and run Spock tests. Testing isn't just about testing the happy paths. We should also check the exceptional cases. Often what we want to do is check that the right sort of exception gets thrown. Let's say we try to create a new polygon with 0 sides. This sounds like something that should cause an error. Let's use F2 to find out what the problem is with the when label. This is the Spock plugin telling us that we can't use this label on its own. We need to give it a then block, which asserts the correct state. In our then block, we want to check that the correct exception has been thrown. We do this by calling thrown with the class of the exception that we expect to be thrown. In our case, we expect a too few sides exception to have been thrown by the call to the constructor. Note that in Java, we'd normally have to add .class onto the end of this to define that this is the type of the exception. In Groovy, we don't need to do this, but you can keep it if you think it makes the code clearer. Let's run this test to see if the behavior of the code is correct. This test does pass. This always makes me suspicious. I like to see a test fail so I know it's really working. Let's change the expected exception to something that doesn't make sense. Let's change it to an array index out of bounds exception and rerun the test. Now the test fails and it tells us that it was expecting an array index out of bounds exception, but it got a too few sides exception. So now we know the code really is doing what we expect. Let's change the test back to be checking for the correct exception. We can even assign the thrown exception to a variable so that we can perform some more checks on it. Let's check the number of sides stored on the too few sides exception to see if it matches the number of sides the polygon was created with. When we run the test again, we can see it's failing on this number of sides. Spock has a really helpful way of showing assertion failures. It not only shows the assertion that failed, but also breaks down the parts into the various values so we can see exactly where the issue is. Here we can see the number of sides stored on the exception is actually 2, when we were expecting 0. Let's go back into our Polygon Java class to see where this problem might come from. Here we can see our too few sides exception was initialized with a hard-coded value of 2, when in fact it should have been sent the number of sides the polygon was created with. Let's rerun our test now. I'm going to use find action, Shift Command and A or Control Shift and A to rerun the test. This time, the test passes. When we're testing a particular path, we sometimes want to check that a known set of values leads to the same result. This exception test is a really good example. We know there's more than one input which should cause this exception to be thrown, and we might want to test all of them. In our case, any integer that is less than 2 should cause the exception. If we're using tests to document the expected behavior, we might want to add the full list of values that can cause the exception, or at least a sample list that demonstrates our expectations. Let's create a new test method that uses data pipes to do this for us. I'm going to copy the previous test because this covers the basic test case, and we're going to expand upon that. In this new test, we add another new label, where, which specifies the input values to the test. For this test, we want to test the constructor with more than one value. So instead of passing in 0, we'll pass in a variable, sides. Our assertion also needs to check the number of sides on the exception matches the number of sides we passed into the constructor. IntelliJ IDEA is underlining this sides variable as it hasn't been defined or initialized anywhere. we're going to do this in our where block. We define sides and then use the left shift operator to give a list of values that we want the int sides value to use. There's a few Groovy things to note here. Firstly, Groovy supports operator overloading, so the left shift operator is used here to show that this is the pipeline of values to use in the test. Secondly, Groovy has a friendly syntax for creating lists of values, which is to simply put the values between square brackets. See what happens when we run this test. It's effectively run 4 different times. The whole test is run once per value in that list. IntelliJ IDEA shows the name of the test, then underneath the test name puts the value of sides for each of the 4 values. All 4 of these runs passed because our code correctly throws the expected exception for each of these values. If we want, we can change the method name to make it easier to understand what's being tested. We can use hash and the name of a data variable in the method name to create a true description. When we rerun this, IntelliJ IDEA shows this updated method name with the value of sides and no extra noise. Let's look at what happens if one of these values causes the test to fail. We know this exception should be thrown for a number of sides that's 2 or fewer, so let's change one value to 3. When we run the test, we can see one of the great things about data-driven testing. All the tests are run even if one of the tests fails. So we can see clearly which cases pass and which fail. If one of them fails, we can see what caused the problem. In our case, the test was expecting an exception to be thrown and it wasn't. Let's go back and fix the test. Data pipes aren't just for testing exceptional cases. We might want to use them to test a series of valid inputs. Let's create another test. Once again, we're going to create a polygon with a specified number of sides. Then we're going to check that the number of sides is the value we expect. We're going to set up the sides variable with a whole list of valid values for the number of sides. When we run this test, we see something similar to the previous test. We see a passing test for each one of the inputs for the value of sides. Once again, if we change one of these to an invalid value, we see this one case fail. In our case, because an exception was thrown, and all the other cases pass. Let's fix the test and rerun it. This test is quite a simple one, so we could reduce the amount of code to do the same thing, if we still think this is readable. We can inline the creation of the polygon, so we call the constructor in the same line as the assertion. If we just have one statement which is set up, test and assertion, we can use the expect label like we did on our very first simple assertion test. Of course, we still need the where block, as this sets all the expected values for the number of sides. Data pipes are a nice way to specify a limited set of data to test. Spock also supports data tables for more complex data-driven testing. As we've seen, it's not unusual to want to pass in a series of values to check the same condition applies to all of them. Often, we may have multiple inputs and want to check them against multiple outputs. Let's say we want to check the calculation of something like the maximum of 2 values, A and B. We'll want to check that the return is the expected maximum value. We use the where to define the inputs to the test. This time, we can lay out a table of values. The first line is the header, the names of the variables we're going to use in the test, separated by a pipe. Then we add a line for each set of inputs to the test. So this first set of inputs might be 1 for A, 3 for B. Then we expect the maximum of these 2 values to be 3. Then we'll check a case where the value of A is the maximum value. Then a case where the values are equal. When we run this test, we see something similar to the data pipes tests. We see a passing test for each of the rows in the data table, described with a method name and the values for each of the input variables. If we make one of these fail, again we can see all the cases are run and we can see one of them fails. Spock's power assertions show the results of calculations, all the input values, and the comparison that failed. We can use this to fix the problem. We can make these data tables more readable by creating a separator between the columns. Let's use IntelliJ IDEA's clone caret feature by pressing Option twice, keeping it held down on the second press, and pressing the down arrow to create a second caret underneath the first. On Windows, this is done by pressing the Control key twice and keeping it held down on that second press. Now if we type a second pipe, it appears on all the lines. This pipe doesn't change the meaning of the test, it simply helps us to understand the table better. In our case, we've grouped the expected output on one side and the inputs on the other. Running the test shows it all working as expected. As before, we can make the test a bit clearer by adding the names of the data variables into the test name. Now, when we look at the test run, it's really clear what's being tested and what the expected result is. Testing real applications can be more complex than simple calculation tests like these. Sometimes we need to mock out classes or APIs to assert the expected behavior. Mocking is built into Spock. We don't need a separate library or framework for mock support. It's also possible to mock concrete classes. If you're used to using other mocking frameworks, you might expect to only be able to mock Java interfaces. But Spock lets us easily create a mock from a concrete class. The given block of a Spock test is the perfect place to set up mocks for our tests. It's clearer then that this is all code that's required to run the test, but is not the code that's being tested itself. Let's assume we want to mock a renderer class, which is a concrete Java class. We can do this either by declaring a variable with type renderer and calling mock without any arguments, or if we prefer to use Groovy's def keyword to define our variables, we'll need to pass the type in as an argument to the mock method. Bear in mind that if you declare it using def, this variable is using Groovy's dynamic typing and so isn't strongly recognized as a renderer type by the IDE or by the code. This is fine if you're not doing much with the mock, but you might sometimes want to specify the type more clearly. This will certainly be more natural for Java developers. Now let's set up a polygon with a given renderer. We'll call a polygon constructor that takes the number of sides and the renderer. We'll pass the mocked renderer in here. In our when section, we'll define the call that's actually the thing we're testing. Let's say that in this test, we want to see what happens when we call the draw method on this polygon. We actually haven't created this method yet. We're doing a bit of test-driven development here. We're writing the test first to define what we expect the behavior to be, then we'll implement the code that makes that test pass. The then block is where we're going to define the expectations. Spock has a nice clear syntax for defining the behavior we expect to see on the mock. In this test, we might expect to see 4 calls on the renderer's drawLine method, given that the polygon has 4 sides. The then block states we expect to see renderer.drawLine 4 times. When tests get a little more complex, sometimes it can be a bit unclear which object is being tested. We can use Spock's @subject annotation to document which object is specifically being tested. This doesn't have any functional impact on the test, it's just to mark the object we're testing. Let's use IntelliJ IDEA to generate the missing methods, just as empty methods, enough to keep the compiler happy. When we run this test now, we'll see that it fails. This is what we expect, because the methods don't do anything yet. We expected to see this drawLine method called 4 times, but it wasn't called at all. Now let's go into the implementation of the draw method. If we make a change to call the renderer's drawLine method in here, and rerun the test, we'll see the test still fails, but this time it says the drawLine method was called once. We want this method to be called for all the sides in the polygon, so we want this call to be inside some sort of loop. We can create this loop a number of ways, for example by using surround with and pressing the number 5 for a for loop. Or we can use a live template. For example, for I will create a classic for loop with index. We can use this to iterate for the number of sides. And let's move the drawLine call into this loop. Now when we rerun the test, it passes. The code is calling drawLine on the renderer mock 4 times. Mocks are a powerful and useful tool to make sure that the code we're testing is calling the APIs that we expect, in the way we expect. Mocks are useful for checking calls out of our code. Stubs are useful for providing data or values into the code we're testing. Let's see an example of a stub in a new test method. Once again, we're going to use the given block to set up the preconditions for the test method. This time, we're going to use the stub method to create a stub of the concrete palette class. Like the mock, you can define it this way, or use def and pass the type into the stub method. Now we're going to set up the stub with the values it will produce when called by our code. We use right shift to state that when the method getPrimaryColor is called, the enum value red will be returned. Now let's initialize our renderer with this stub palette. Again, we can mark this as the subject of our test if we want to. I'm going to use an expect label because my test and the assertion are combined. I expect that when I call getForegroundColor, this will return color.red because I'm using this test to state that I expect getForegroundColor to return the same color as the palette's primary color. Once again, we're using test-driven development here. We've used the test to drive out what we expect the methods to look like, but they don't exist yet. Let's get IntelliJ IDEA to create the most basic method for getForegroundColor that makes the code compile. Now let's run the test. It fails, of course, because we haven't implemented getForegroundColor. It just returns a null value. However, it's good to see the test fail first. It usually indicates the test is checking the right thing, even if that right thing hasn't been implemented yet. Let's go into the getForegroundColor method and get it to return the palette's primary color. Now, when we rerun the test, it passes. The test injects a stub palette into the renderer. We tell the stub palette what to return when the getPrimaryColor method is called, so we can check that the renderer does what it's supposed to do when we call getForegroundColor. If we had set this up as a mock instead of a stub, this would have worked as well. Mock objects support the mocking behavior we saw in the previous test and the stubbing behavior we saw here, whereas stub objects only support stubbing and not mocking. My preference is to keep stub and mock behavior separate where possible, so it's usually best to use stubs just for stubbing and mocks only for mocking. We've now covered all the key features for creating and running tests with Spock. In the next few sections, we'll look at additional features that can help you write short, descriptive, correct tests. When tests get big, we may want to split out large parts of code or common code into helper methods. Let's say we have a test like this one. It uses a shape factory to create a default shape, and then we perform a number of checks to make sure this meets our expectations. You can imagine in real production code there might be a lot of values to check here, not just the 2 we have here. We may be tempted to move all these checks into their own method, especially if they're going to be used by more than one test. If we do this and rerun the test, it will pass. However, let's check it's passing for the right reason. Let's change an assertion so it should fail and it still passes. This helper method is not doing what we expect. If we move our assertions into a helper method like this, it can no longer use the comparison operators to define the expected behavior. Instead, we need to add the assert keyword specifically. Now, when we rerun, we should see the test fail. There's something else to be aware of too. It fails on the first assertion that fails. It never runs the assertion to check the polygon's renderer. Later in this video, we'll look at how to address that. For now, let's make this test pass again. This time it's passing for the correct reasons. We can also accept IntelliJ IDEA's suggestion that this method is static if we want. Let's look at an alternative approach to testing multiple properties of a single object. Let's reset the previous test back to how it was before we introduced the helper method. We can use Spock's with and a closure to check multiple values on the polygon. Inside this closure, we don't have to say polygon dot, we just assert the property matches the expected value. Let's change this so it fails so we can see how it works. As with the helper method, if the first assertion fails, it doesn't run any further assertions. This might be what you want from your test. If one value is wrong, the whole test should fail regardless. But sometimes we want to run all the assertions so we can see exactly what's working and what's not. Let's look at how to make sure all our assertions are run regardless of whether one of them fails. We can replace our with call with verifyAll instead. Let's run this and see what happens. This time, not only does the number of sides assertion fail, but the check on the renderer also fails. With verifyAll, we will run all assertions and see which fail and which pass. This can help us when we're iterating quickly between writing and fixing tests. Let's go back and fix this test. And let's rename it so it correctly states what it's doing now. Note that with the string method names, we can easily add quotes and other special characters. Let's look quickly at methods for setting up and tearing down data and state for our tests. If you've used other testing frameworks, the concept of a test or specification class setup and teardown will be familiar. Spock provides a setup method, which we can generate with IntelliJ IDEA, which will be run before every individual test method in this class. This can be used to set up a clean state at the start of each test. To clean up data or state at the end of every test method, you need a cleanup method. This is run after every individual test method. Use the setupSpec method to set up state once at the start of the specification. This is for things that should not change between individual test methods. Create a cleanupSpec method for final teardown code. This method will be called once at the very end of running all the tests. I like to move all my cleanup code to the end of the specification class since they're run at the end. One final piece of useful information here. The tests in this tutorial created the objects they were testing in the test methods themselves. However, you might also want to create your test instance as a field in the test. You can use the @subject annotation on this field to show this is the object under test. You can then reference this field in the test methods just as you'd expect to in any Java or Groovy class. Let's take a look at one last feature to help document the requirements via tests. We've seen that Spock has a focus on readability and tests as documentation. The subject annotation, the test labels, strings as method names, plus all you can do to customize these string values, all contribute to being able to use the automated tests as documentation for what the system should do. We can also add more information, again for readability or documentation purposes, to the blocks in our tests. We can add a string value here that gives a more detailed description of this block. If we want to split a block into further blocks, for readability or to add documentation, we can use the AND label. This is just to let us break things up further. The text is available to the Spock runtime, so these messages can be used in messages and reports. Spock is powerful and has even more to offer than we've looked at here. Believe it or not, we've only touched on the surface of what Spock can offer. We've seen the basics of a test. We've seen how to use labels to define tests. We've seen the power of data-driven testing. If you want to find out more about Spock, take a look at the excellent reference documentation. Some of the examples you saw in this video came from there. But there is also a lot more depth of information. There's also a Spock primer, which is a great place to start with Spock. Thanks for watching.